Hi students, this lecture is on chapter 14, which is on the ideal gas law and the kinetic theory of gases. Okay, so what we've seen so far, well, actually saying the development of thermal physics, we have to remember that thermal physics started right around the 1700s, and honestly, you know, it is based upon 4 laws of thermodynamics. However, and I've given you 2 of the 4. I gave you the 0th law of thermodynamics, and I gave you the 3rd law. 0th law of thermodynamics allows us to take a temperature. That's the theory. That's the law of thermodynamics that controls thermal equilibrium. And of course, the 3rd law of thermodynamics says that a system can never be taken to absolute 0. But for most of the history of, probably like the first 100 years or so of thermodynamics, it was really based. It was a purely energy theory. And it was based upon what we'll talk about in chapter 15 as the 1st and 2nd laws of thermodynamics. And so, and as I've said before, you know, at least with you know, in comparison with development of mechanics, we start off with the players. We start off with the objects that are moving. We understand how those objects move. And then we develop laws of physics, or we discover and apply laws of physics, then we apply an energy concept afterwards. Well, with thermodynamics, we have to do things backwards. We don't know, we can't see, and we don't even know if the players that make up the thermal system even exist. You know, we did not actually have confirmed knowledge of the existence of atoms until 1830. All right, so we have to start off with an energy theory. And so thermodynamics really is about the only major area of physics where you can actually do pure thermodynamics and not have any knowledge of an atom. And that's, you know, you can't say that about practically any other field of physics. Why? Because thermodynamics was formed as a pure energy theory, and we did not even understand or even know about atoms. All right, so kind of going back to the concept of atoms, you know, we did not know about atoms until 1830. So 1830, you know, and this kind of drives people like me crazy because, you know, scientists are always kind of wonder when they're going to get their special break and make a big discovery. And then when you see about a scientist who actually trips over a discovery, it's kind of irritating. But that's what happened with the discovery of the atom. So in 1830, a botanist of all people, a botanist from Scotland by the name of Robert Brown, went to his lab. And here, changing pens here. So in 1830, Robert Brown a botanist from Scotland set up an experiment with pollen grains in a suspension. Some sort of a soup, if you will. And what he noticed is in his microscope was something very interesting. The pollen grains performed random dances. They're moving about in random ways. Robert Brown was smart enough to understand what that was all about. He understood that was the atoms, the unknown atoms, colliding with these pollen grains. You can't see the atoms, but you can see the pollen grains. It's like if you imagine, before COVID-19, you would have you might go to a summer concert out in the park or out in a field someplace, and the band's playing, and somebody gets a beach ball out there and starts pushing it around. So you hits the beach ball, and then somebody else in the crowd, and eventually comes to you. You just give it a random push. You push it out, and then somebody else in the crowd, pushes it. So they're all just having a good time. They're relaxing, and they're pushing this beach ball around, right? Well, let's just imagine for a moment that you can see the beach ball, but you can't see the people. All right, so there's this beach ball. There has to be something causing it, giving it, imparting forces to it, because the beach ball is changing momentum. When you have a change in momentum, there must be a force being applied. It's basically, momentum is a force is a time rate of change of momentum. So momentum is a momentum of the beach ball is changing. There must be forces applied to it. All right, and so this is really this is a monumental experiment. The very existence of an atom was in question. It was hotly debated, and there are people who are solemn believers in atoms, and those who were solemnly disavowed the very concept of atoms. And so this was something that was a great debate, and this very experiment put all that to rest, that yes, atoms do exist. And so with that, thermal physics was able to move on to its next step. And then we'll talk. So this next step we'll talk about is the kinetic theory of gases. But before that, and that's where we're leading in this lecture. Before that, we understood that we had a concept of what's called an ideal gas. Okay, so this is something that we can see with experiment. And so don't need a knowledge of atoms yet. We understand this whole concept of an ideal gas. All right, an ideal gas, as the name implies, ideal, is a gas. Gas doesn't necessarily mean always a phase of matter. What it really means is an arrangement or assortment of particles. Particles that are separate from each other, that are just moving around. You can have a gas of atoms. You can have a gas of molecules. You can have a gas of electrons. You have a bunch of particles moving about in a space. That's called a gas. Right, so we see it as a phase of matter, but in a more general sense, it actually is a statement of it's a description of particles that are usually contained in a vessel of some sort that are moving around. So, like I say, so I say a gas, an ideal gas is a gas in the sense of a bunch of atoms or molecules. We're going to think of monatomic ideal gas right now. So, an ideal gas is a gas of atoms or molecules such that the spacing, the interatomic or in the case of molecules, the intramolecular, spacing is so large that the constituents never collide with each other. If they do collide, then that would be a force of interaction, which could cause liquefaction. So an ideal gas is really, some people refer to it as a perfect gas. It is a gas that is an idealization. So it's a gas where the spacings between whatever it is, the constituents, atoms or molecules, whatever it is so large that the constituents never collide with each other. They only collide with the walls, not with each other. If two atoms collide, then they experience interatomic force. If they experience a force, that would cause possible liquefaction. So in this case, we don't want any kind of percent liquid or liquefaction. We want purely an ideal gas. Okay, if that's the case, if you can make that assumption that or if these conditions are true, then the following equation of state holds. So if the conditions of an ideal gas hold, then the following equation of state is true or applies. And that is the pressure times the volume is equal to the number of constituents times this constant called the Boltzmann constant times the absolute temperature. Okay? Now, the pressure is the absolute pressure. Now, we talked about pressure back in thermal physics, and we talked about gauge pressure and atmospheric pressure. Well, the absolute pressure, remember gauge pressure, tire gauge, when it was solely flat, reads 0. Because gauge pressure reads 0 atmospheric pressure. But absolute pressure is the total pressure. So the pressure absolute is equal to pressure atmospheric plus the pressure gauge. Okay? V is the volume, so this is usually in pascals. Newtons per meter squared. Pascals is usually the unit. V is the volume. Volume of the gas, that's usually in meters cubed. Okay? K is a special constant of the universe that is called the Boltzmann constant, named after the great thermodynamicist Ludwig Boltzmann. So that's 1.38 times 10 to the negative 23 joules per Kelvin. That's the Boltzmann constant. Okay. T is absolute temperature. Got to be in Kelvin. Kelvin temperature. And N is number of constituents. That's usually a huge number, like 10 to the 23. All right, that's usually a huge number. It's usually in a typical gas, there's usually a tremendous number of constituents. All right, PV equals NKT. All right, now you might say to yourself, well, I'm taking chemistry, and that doesn't look like the ideal gas law that I saw in my chemistry class. Well, I'll show you that it actually is. So again, keep this in mind. We'll do some examples here to kind of warm up these concepts. But we have to talk about a concept first that if you've taken chemistry, you've seen in your chemistry class, and that's the concept of what's called a mole. All right, so a mole is defined to be the amount of a substance that contains as many atoms or molecules as there are atoms in exactly 12 grams of carbon-12. Grams or 0.012 kilograms of carbon-12. So you determine carbon-12, you determine exactly how many atoms are in carbon-12, exactly 12 grams of carbon-12. You actually find out that that number is called Avogadro's number. So there's this many of them. N sub A for Avogadro, 6.02 times 10 to the 23rd. That's how many atoms in 12 grams of carbon-12. Okay, this is called Avogadro's number. Named after Amadeo Avogadro. All right, so Amadeo Avogadro who lived from 1776 to 1856. Great, he's an Italian scientist. All right. So what does this mean? Well, it means that we've defined some sort of a special number. We can count by that number. Now, why do we choose carbon-12? Well, just like we humans find water to be so important. Water is one of the most important substances to us. So we define a temperature scale after the Celsius temperature scale. It's defined such as 0 degrees Celsius is freezing and 100 degrees Celsius is boiling. Well, that's because water is so important to the human race. Well, in the case of carbon-12, anything that is alive has carbon-12 in it. In fact, it's based on carbon-12. All life forms that we've ever seen on the Earth are based on carbon-12. Carbon-12, if you look at the periodic table, is in such a place where it forms extremely well with other atoms, and it's very good at building up polymer chains, proteins, sugars, alcohols, you name it. And so and in fact, life is formed based upon carbon-12. In fact, if anybody who's taken or we'll take organic chemistry. Organic chemistry is the chemistry of carbon-based substances or life forms. Biology, again, to do biology, you have to have carbon-based life forms. Hypothetically, if you look just below carbon on the periodic table, you see silicon. Hypothetically, there might be some place in the universe that has silicon-based life forms. Silicon should have the same properties of carbon. We have never seen on Earth a silicon-based life form. Not to say that they don't exist, but we've never witnessed one, right? So we use carbon-12, which is so important to us because of life science, and that we use that as a way of, really, it's a way of normalizing your numbers. Instead of having gargantuan numbers like capital N, instead you can speak in terms of moles. So a mole is really a number of things. It's like a dozen. I can have a dozen eggs, I can have a dozen shoes, a dozen people, a dozen books. A dozen just means 12. It's just a number of something. Well, and there's historical reasons for why 12 is important. However, we've chosen a way of talking about a number of atoms. We have these giant numbers of atoms. We really like to talk about 3 moles, 5 moles, 17 moles, some handleable number of, some handleable number that we can use in chemistry and atomic physics. And so what we can do is we can express numbers in terms of moles. All right, and so we can fix up the ideal gas law in that manner. What we can do is we can say, okay, well, we have this Avogadro's number, and I told you the ideal gas law looks like PB equals NKT. All right, and oftentimes I refer to this as the physicist form of the ideal gas law, even though the physicists use the other form as well. Well, let's do the following. Let's multiply the right-hand side of the equation by 1, but 1 that looks like n sub a over n sub a. So I'm going to multiply the right-hand side of this equation by n sub a over n sub a. I mean, basically a fancy way of multiplying by 1. I can always multiply by 1. No one says I can't do that. It's Avogadro's number over Avogadro's number. What I'm going to do is I'm going to put the denominator of Avogadro's number just underneath n, cap n. So we'll write PV, we have cap n over n sub a. And I'll put the other Avogadro number, and the one in the numerator, I'll stick it right next to K. So I'll put this K n sub a. Then I have still the temperature T. Cap n over n sub a, number of constituents divided by the number of constituents per mole, gives me moles. So I usually use little n for that. Cap n over n sub a, this is number of moles. And if I calculate K times n sub a, K times n sub a, well, let's see, Boltzmann's constant, 1.38 times 10 to the negative 23 joules per Kelvin times 6.02 times 10 to the 23, and that's per atom, or per mole, sorry. I find out that I get what I would oftentimes see as capital R. Call this capital R, and it might be familiar to you. It's 8.31 joules per mole Kelvin. Great. So what I can do is, instead of cap n over n sub a, I can substitute that for little n, and K times n sub a, that could be R. And so what I can actually rewrite the ideal gas law, I can simply rewrite as cap n over n sub a is little n R T. And so what you remember in your chemistry class is PV equals nRT. But we also could say that we have two forms. PV is NKT. So again, this is where you're talking about the number of constituents, the actual raw number of atoms or molecules as in your ideal gas. Here you're talking about the number of moles. And so you have a number that's smaller because it's all being divided by 6.02 to the 10 to the 23rd. So you'll have numbers like 3 moles or 7 moles or something like that. Whereas here you're going to be talking about numbers that are like 10 to the 21st or 10 to the 22nd, 10 to the 23rd, things like that. So again, that's so the form of the ideal gas law that you saw in your chemistry class is pretty much the same form as that you get taught here looking at the atomic perspective. Okay, so let's work some problems. That's all I really have to say about the ideal gas law. Just give it to you. Okay, so OpenStax 13.22. That says the gauge pressure in your car tires is 2.50 times 10 to the 5th pascals. At a temperature of 35.0 degrees Celsius. When you drive it onto a ferry boat, to Alaska. What is their gauge pressure later? When their temperature has dropped to negative 40.0 degrees Celsius. Okay. OpenStax 13.22. The gauge pressure in your car tires is 2.50 times 10 to the 5th pascals at a temperature of 35.0 degrees Celsius. When you drive it onto a ferry boat to Alaska, what is their gauge pressure later when the temperature has dropped to negative 40.0 degrees Celsius? So again, it's like you're driving down to a ferry boat, let's say in Seattle, at a warmer temperature on a hot day, and then you take the ferry boat all the way to, let's say, Fairbanks, Alaska, or actually Fairbanks is more inland, but you take your to Alaska where the temperature dropped to negative 40. All right. So now we're going to assume that the air in the tires is an ideal gas, and we're also going to assume that a number of molecules of air or number of moles of air is not going to change. All right, it's going to have a constant. There's no air is going to leak out. And no one's going to pump any air into the tire. All right. Okay. So let's imagine initially we have. So we're going to assume air in tires is an ideal gas. And that the number of moles of air in the tires is constant. Okay, so what does that mean? Well, it means I have an ideal gas law initially when the car is, let's say, in Seattle. P1 V1 is NR T1. Later on in Alaska, P2 V2 is NR T2. All right. However, we don't expect the volume of the tires. I mean, we expect that there to be a negligible change in the volume of the tire. So we expect a negligible change in the volume of the tires. So we can say that V1 equals V2 equals, say, V. All right, and so effectively we can take the subscripts off. We say they have the same volume. So what we can do is we can set each of these equations equal to what is constant between them, and so we can say that we have NR over V is equal to P1 over T1, or we'll say P2 over T2 is P1 over T1. All I did is I set each of these equations to what they have in common. I can eliminate that. What I now have is just the relationship between pressure and temperature at this point. All right, and what I can then do is multiply top and bottom, or multiply each side by T2, and I can get an equation that's P2. I got a fraction of temperature, T2 over T1 times P1. Yeah, that's all the math you have to do. Now, the issue is I have to get absolute pressures and absolute temperatures, all right? So there's the equation I need, all right? Now I have to convert pressures and temperatures. Everything has to be absolute for the ideal gas law. So I'll rewrite all this. I'll put this up higher. I got a real estate challenge, so. Okay, so again, my equation is P2 is T2 over T1 all multiplied by P1. All right, so I don't know P2. I do know P1. I know it's gauge. I need to remember the atmospheric pressure is 1.013 times, so again, P1, let's be real here. So P1 is, I have it as gauge. I need it as absolute. So that'll be P atmospheric plus P1 gauge, or 1.013 times 10 to the 5th pascals plus 2.50 times 10 to the 5th pascal. You add this up, you get the P1 is 3.51 times 10 to the 5th pascals. Okay, that's the absolute pressure of the air in the tires over in before you left to go to Seattle. I'm sorry, before you left to go to Alaska. Let's say you're in Seattle, going to Alaska. All right. Now the temperature where you're taking off. Well, we're told it's 35 degrees Celsius. Well, we don't want Celsius. We want absolute. We have to add 273 to that, and so what we'll get is 308 Kelvin. And then the temperature in Alaska. is negative 40 degrees Celsius. But again, we don't want degrees Celsius. We want Kelvin. So negative 40 plus 273, that'll be 233 Kelvin. All right, those are the values that we need in this equation. Everything has to be absolute. Okay, P2. Going to the equation, it'll be T2 over T1. What's that going to be? It's going to be 233 Kelvin. And again, do not put Celsius in here. Over 308 Kelvin. Okay, and then multiplied by 3.51 times 10 to the 5th pascals. P2. Do this, ends up being 2.66 times 10 to the 5th pascals. But this is an absolute pressure. Now again, the general way of doing things in physics is how you're given a problem is how you return it. All right, you're given the problem in terms of gauge. You should return it as a gauge pressure. So I should return this as P2 gauge. Well, that's easy to do. P2 gauge will be P2 minus P atmospheric. Or P2 gauge will be the 2.66 times 10 to the 5th pascals minus 1.013 times 10 to the 5th pascals. Finally, I would end up with P2 gauge equaling 1.65 times 10 to the 5th pascals. And there you go. Application of the ideal gas law. Okay, do another problem. OpenStax 13.24. All right, that says, suppose a gas-filled incandescent light bulb. Incandescent light bulb. Is manufactured so that the gas inside is at atmospheric pressure. When the bulb has a temperature of 20.0 degrees Celsius. A, find the gauge pressure inside such a ball, when it is hot. Assuming its average temperature is 60.0 degrees Celsius. An approximation. And neglecting any change in volume due to thermal expansion or gas leaks. Oh. See, my still on camera. All right, and then B, the actual final pressure for the light bulb will be less than calculated part A. Because the glass ball will expand. We want to find out what the actual pressure is. So amount of room. So again, that'll be what part B is about. All right, so suppose a gas-filled incandescent light bulb is manufactured so that the gas inside is at atmospheric pressure when the bulb has a temperature of 20.0 degrees Celsius. A, find the gauge pressure inside such a bulb when it is hot, assuming its average temperature is 60.0 degrees Celsius, an approximation, and neglecting any change in volume due to thermal expansion or gas leaks. And B, the actual final pressure of the light bulb will be less than that calculated in part A, because of the glass will expand. So we're going to try to figure out what the actual pressure is, allowing for thermal expansion. I can't write that all on here, and to see if that's even worthwhile doing. All right, that's what part B is about. All right, so let's do it part A. Fairly lengthy problem to write down. All right, A it is. Let's see. So we know initially the temperature is 20 degrees Celsius. Well, we want to work in absolute temperature, so 20 plus 273 or 293 Kelvin. Likewise, where the bulb will be heated to 60 degrees Celsius temperature, and we don't want to use Celsius, we want to use Kelvin. 60 plus 273 or 333 Kelvin. And we also know that P1 is P atmosphere. Or we can say is 1.0 atmosphere. Or 1.01 times 10 to the 5th pascals if you want. All right, so again, you're going to want to take the situation where the light bulb is at its 1 atmosphere and 20 degrees Celsius. And then the ideal gas, again, we're going to assume an ideal gas. And again, that's P1. And again, the situation at when it's hotter, when it's hot. Okay, now for part A, so again, assuming ideal gas. Now it's this part A is going to seem very, very similar to the previous problem we did. In part A, so we're going to assume that the glass bulb does not expand for part A. Again, this is part A. So i.e. V1 equals V2 equals, say, some common V. And just like the last problem, we make that assumption. So that means that the two ideal gas laws, the volumes are the same. And because I made that assumption. And then deja vu, I'm going to do the exact same thing I did before. I'm going to solve both of these ideal gas law equations for what is in common. And again, that's NR over V. And of course, just like last time, I say, well, that's equal to P2 over T2 and P1 over T1. Again, same as the ferry boat problem with the tires. And just like last time, I've eliminated NR over V. So this is my actual equation, just pressures and temperatures, and I can solve for P2. P2 is T2 over T1 times P1. And deja vu, it already did the same mathematics as before. And we can put in here the temperatures, and we have a unitless number. So we have P2 is 333 Kelvin divided by 293 Kelvin. Now that I have a unitless number, I don't really have to bother converting the pressures. I can keep them in atmospheres. I'm going to take a pressure times a unitless number and get another pressure. Given that it's, the T2 over T1 is a unitless number, I don't have to really worry about multiplying numbers, variables together to give me some other SI unit. I'm really taking a variable multiplying by a unitless number, so I can just keep the pressure in atmospheres if I still choose, and I'll do that. So the pressure I'm going to keep is 1 atmosphere. I'm not going to bother putting in SI just to take it back to 1 atmosphere because it was given to me in terms of atmosphere. So if I do this, I find out that my final absolute pressure, if I don't consider that the glass bulb will expand, will be 1.136 atmospheres. But I want this in gauge, right? So really the initial gauge pressure is 0 when it's at 20 degrees Celsius. At 60 degrees Celsius or 333 Kelvin, the total pressure is 1.136, or gauge, and very similar to last problem. P2 gauge is P2 total minus P atmosphere, or P2 gauge is 1.136 atmospheres minus 1.00 atmosphere. So the answer to my first question, P2 gauge is 0.136 atmospheres. That is the answer to the first question. That is if I do not consider that the glass bulb has thermally expanded. Okay, so let's remember this answer, 0.136. Now, let's now consider that the glass bulb actually does expand, but it doesn't matter. Is it going to really change my answer to P2? All right, so we're going to now allow for thermal expansion. We have to go back to chapter 12 for a moment. So again, let's just remember this number, 0.136. And we'll calculate P2 gauge considering volume expansion of glass and see if it matters. So let's go back to chapter 12 briefly and say, okay, well, what was that equation? Oh, that's right. Glass or anything changes volume. Delta V is given as the initial volume, V naught, times a volume thermal expansion coefficient, beta, times delta T. And that's the empirical relationship talked about volume expansion. We had one that was for linear expansion as well. We would just put L's here. Delta L was L naught alpha delta T, right? And so again, we found out that beta is typically equal to 3 alpha. All right, so again, going back to chapter 12, this is an empirical relationship for volume thermal expansion. All right, I need to look up some numbers here. So beta, I need to look up beta for glass. Well, beta for glass is going to equal 27 times 10 to the negative 6 per degree Celsius. That's for glass. Okay, I have to look that up. Delta T, what's that? Well, delta T is going to be the 333 Kelvin minus the 293 Kelvin, and that's going to be 40 Kelvin, which, by the way, when you given that the increments in Kelvin are the same as the increments in degrees Celsius, we actually can do this delta T problem. We really need to do it in terms of degrees Celsius because the beta is in terms of degrees Celsius. So remember, an increment in degrees Celsius is the same as an increment in Kelvin. They're the same size increments. The Kelvin scale and the Celsius scale are just different by an offset. So I can write that 60 degrees Celsius minus 20 degrees Celsius is 40 degrees Celsius. So what I really want to do is I'm going to take this equation. I really want to talk about the fractional change in the volume expansion. So delta V over V naught. I'm going to divide both sides of the above equation by V naught, and I'll get beta delta T. So the fractional change in volume. All right, so what's that going to be? That's going to be 27 times 10 to the negative 6 per degree Celsius times 40 degrees Celsius. So degrees Celsius cancels out, and this is a pure number as you would expect it to be. So delta V over V naught is going to equal a very small 1.08 times 10 to the negative 3. That is your volume expansion, the fractional expansion. Very, very small expansion of the volume, relatively. Okay, let's keep this in mind, keep this number in mind. All right, now, so we'll put it in the parking lot. Delta V over V naught was 1.08 times 10 to the negative 3, and it is unitless. All right, now, going back to the ideal gas law. Well, we have the initial situation where the say B naught, where the temperature or where the uh, glass bulb is at 0 degrees Celsius, not stressed at all, and that'll be nRT1. Then you have the situation later on where I have P2. Now I have an expanded volume. The volume has expanded by what? It was what it was before, V naught, plus a little additional delta V. It's expanded. It's been a volume expansion caused by the temperature increase. And that'll be nRT2. So again, my ideal gas laws, I can't just say that the volumes are the same. Now they're going to be, they're going to start off with the initial, but this is the initial volume, but this is the initial volume plus a delta volume. Why? Because of the volume expansion. All right. Now, what I want to do over here is I'm going to do what I did before. I'm going to divide both sides by V naught. So over here I'm going to divide the left side by V naught, and what I do to the left, I want to do to the right. So I can do is I can take that division, I can actually distribute it to the distributive property. So I have V naught over V naught, which is 1 plus delta V over V naught. And that's going to equal nR over V naught times T2. Okay. Now, I can take a look over here and say, oh, well, let's see here. nR over V naught on the other ideal gas law, well, that's going to be what? P1 over T1, right? So why don't I just substitute now for nR over V naught? We can substitute over here from the other ideal gas law, and we can write that P2 times the quantity 1 plus delta V over V naught is P1, or basically I can write this as T2 over T1 times P1, like I had before. But now I have this expanded volume, and what I can do is I can solve for P2. P2 then becomes on the top T2 over T1 times P1, all divided by 1 plus delta V over V naught. All right, and so that's my new form or equation to calculate P2, allowing for thermal expansion. So let me write this further up, and we'll put numbers in and see what happens. So we have P2 is T2 over T1 times P1, all divided by 1 plus delta V over V naught, which I did up there. So put in some numbers. So P2, T2 over T1, what was that again? That was 333 Kelvin over 293 Kelvin. And then P1 was 1 atmosphere. And I can still do that because I'm multiplying by a unitless number. And oh, by the way, I'm dividing by a unitless number as well. 1 plus this unitless number. So everything's unitless, and I can just keep P1 as atmospheres. Now on the bottom, I'll divide by 1 plus 1.08 times 10 to the negative 3. When I do all of this, I come to find out that P2 now becomes 1.135 atmospheres. or P2 gauge is P2 minus P atmosphere, or P2 gauge is 1.135 atmospheres minus 1.00 atmospheres, and I get P2 gauge equaling 0.135 atmospheres. Now remember, comparing with part A, where I didn't do the extra correction due to volume expansion, I got 0.136 atmospheres. So basically there's a difference in the third decimal place. So this means that it's irrelevant. So it is irrelevant, or it is not, or the change in P2 due to volume expansion of the bulb is negligible. So it means I really don't have to do that. It's more than what I actually have to do. I don't really have to actually consider the volume expansion of the bulb. All right. Let's do 13.28 of OpenStack. All right, calculate the number of moles in a 2.00 liter volume of air. In the lungs of an average person. Note that the air is at 37.0 degrees Celsius. Which is body temperature. Okay, calculate the number of moles in 2.00 liter volume of air in the lungs of an average person. Note that the air is at 37.0 degrees Celsius body temperature. All right, so again, we're going to go to the ideal gas law. We'll assume that the air in the lungs is an ideal gas. So assume that the air in the lungs is an ideal gas. So it must obey the ideal gas law. P V equals nRT. All right, so, and we want the number of moles, so we can solve for that. N equals PV over RT. Well, the pressure we assume is 1 atmosphere. Got to put everything in absolutes. I'm multiplying things together now. So pressure is 1 atmosphere, which is 1.01 times 10 to the 5th pascals. Must be absolute pressure. The volume, well, it's 2 liters. We know that a liter equals a decimeter cubed. There's 1 decimeter cubed per liter. And there's 0.1 meters in a decimeter. Don't forget to cube that. So the volume is going to be 2.0 times 10 to the negative 3 meters cubed. And the temperature, 37 degrees Celsius. Well, we don't want to do Celsius. We want absolute. So add 273, and you get 310 Kelvin. That's what we need. So N will be 1.01 times 10 to the 5th. Let's try to fit this over here, I guess. N is 1.01 times 10 to the 5th pascals, that's 1 atmosphere, times 2.0 times 10 to the negative 3 meters cubed, divided by 8.31. Gas constant, joules per mole Kelvin, divided by 310 Kelvin. And if I do all that, I find out that N equals 7.84 times 10 to the negative 2 moles. All right. Abbreviation for moles is MOL, which is a direct application of the ideal gas law. Okay, we'll do one more problem for the ideal gas law, so we'll move into kinetic theory. I want to do OpenStax 13.38. Okay, that says in deep space, between galaxies, the density of atoms is as low as 10 to the 6 atoms per meter cubed. And the temperature is a frigid 2.7 Kelvin. Okay, what is the pressure? B, what volume in meters cubed is occupied by 1 mole of gas? C, if this volume is a cube, what is the length of its sides in kilometers? Okay. Opus Acts 13.38. A, in deep space between galaxies, the density of atoms is as low as 10 to the 6 or a million atoms per meter cubed. And the temperature is a frigid 2.7 Kelvin. What is the pressure? B, what volume in meters cubed is occupied by 1 mole of gas? And C, if this volume is a cube, what is the length of its sides in kilometers? So again, we're talking about a very, very rarefied type gas. I mean, very, very non-dense, very sparse. All right, here we go. Now, I like this problem because we're going to kind of see a different version of the ideal gas law. Now, we've seen density before, and we talked about mass density, but there's also a number density. And that's the number of something per unit volume. So we see that the number density rho is 10 to the 6th per meter cubed. That's 10 to the 6th atoms per meter cubed. It's a number density, not a mass density, but a number density. It's different kinds of density. The absolute temperature in intergalactic space is a frigid 2.7 Kelvin. Okay, so what's the ideal gas law? Well, again, it's going to be PV is NKT. Let's divide both sides of the equation by V. So P, and I'll put the V underneath the N. So I have N over V KT. N over V, that's the number per unit volume. That's my number density. So P, another version of ideal gas law, is rho KT. All right, and so we have everything we need. Rho is 10 to the 6th per meter cubed. K, 1.38 times 10 to the negative 23 joules per Kelvin times 2.7 Kelvin. P is going to be very, very small, 3.7 times 10 to the negative 17 pascals. You did everything else in SI, your answer should be in SI, or pascals. There's part A. It's very, very low pressure. 3.7 negative 17 pascals. Okay, let's look at part B. Well, part B says what volume is occupied by 1 mole of the gas, right? So we know that it's going to be basically just a proportionality problem. We know that 1 meter cubed of the gas contains 10 to the 6th atoms. Question is, what volume V prime of gas contains a mole, or 6.02 times 10 to the 23 atoms? Well, when you do that calculation, you find out that V prime is simply going to be 6.0 times 10 to the 17th meters cubed. So that is how much volume you would need to have enough atoms in this very, very sparse gas to equal a mole. Very large volume. Well, if you were to make a cube with that volume, how big would that cube be? So again, let's remind ourselves of parking lot this. So we're going to do part C now. Parking lot, that a mole of these atoms requires a volume of 6.0 times 10 to the 17th meters cubed. Now, if we imagine that that volume happens to be a cube of side length S, how big would that cube have to be? So we know that a volume of a cube is S, the width, the length, and the height. All of these are S. The volume of a cube is S cubed. Length times width times height, but all of these lengths are the same because it's a cube, the perfect cube. And that's equal to 6.0 times 10 to the 17th meters cubed. What do? You take the cube root of both sides, right? So I get S, but again, the cube root of the right side is 6.0 times 10 to the 17th meters cubed, but I'm taking the cube root. I'm taking the cube root, or the 1/3 power of each side. If I do that, I find out that if this volume was a cube, it would have a side length of 8.40 times 10 to the 5th meters, or divided by 1,000, it would be 840 kilometers. So we would have to have a cube that each of the sides is 840 kilometers in order to have a volume large enough to contain 1 mole of these intergalactic atoms. That is how sparse these intergalactic atoms are. All right. Well, that is the ideal gas law. So now let's go to the next topic, the second of 2 topics in this lecture, and that is the kinetic theory of gases. So again, it is my great pride to talk about the kinetic theory of gases. So in 1830, really not that long ago, we had the first direct evidence of atoms because of the work or the discovery by Robert Brown, it's called Brownian motion. So Robert Brown discovered atoms, or discovered the existence of atoms. In 1830, with the observation of what's called Brownian motion. That's this dancing of these pollen grains because of being run into by atoms. Now put that in perspective. You know, my father was born in 1930. So there are probably a few centenarians around at the time of his birth who were around just before Robert Brown did this discovery. So this is not a very old this is not very old knowledge in the grand scheme of things. So Richard Feynman, somebody you ought to look up and read about, highly interesting physicist, and many people refer to as the greatest physicist since Albert Einstein. There's a main biography written about him called Genius, Life and Science of Richard Feynman by James Gleick. Richard Feynman was once asked. Now, so Richard Feynman won, besides winning 1965 Nobel Prize in Physics for quantum electrodynamics, which is the quantum mechanically correct electrodynamics. He also is noted for developing the greatest, really the first ever overall freshman sophomore treatment of physics. He did it for the students at the California Institute of Technology, or Caltech, and and this is called the Feynman Lectures on Physics. I mean, you can buy them at any Barnes & Noble or on Amazon. They are a brilliant, brilliant work of physics. Well, somebody asked Feynman one time if, for some reason, all of the knowledge of science were to be lost in a great cataclysm, save one item, what would that item be? And Richard Feynman replied that it would be that all things are made of atoms. For him, he said, if I knew all things are made of atoms, then I can then derive everything else. And maybe Richard Feynman can do that, but most people clearly would not be able to do that. But for him, I mean, he's one of the greatest physicists ever. For him, this knowledge that all things are made of atoms is greater than any other knowledge, and yet this knowledge is so young. I mean, 1830 is not that long ago in the grand scheme of things. All right, and so now later on, Albert Einstein, in one of his great papers in 1905, and I'll talk more about Albert Einstein in physics too. Albert Einstein was able to get a theoretical understanding of Brownian motion. So Einstein wrote four seminal papers in 1905. 1905 was oftentimes called the year of miracles, or the annum mirabilis, as it's been called, where Albert Einstein came out of nowhere and wrote 4 Nobel laureate papers, Nobel laureate level papers. 2 papers where he was able to derive the special theory of relativity, where he overturned Isaac Newton. 1 paper where he was able to get a theoretical description of Brownian motion, and 1 paper where he was able to show that light was not only a wave, but it was also composed of energy packets or particles called photons. And he was able to show you experimentally through what's called a photoelectric effect how you even get the photons. So not only was he able to predict it, he was able to tell you how to set up an experiment to actually prove it for yourself. So all this. So again, Einstein, was able to give the first theoretical understanding of Brownian motion. So with the understanding of atoms, or being excited by the fact that we now know that atoms exist, one of the other great stalwart physicists in history. So if we're talking about the 3 greatest physicists in history, it would be Albert Einstein, James Clerk Maxwell, who I'm about to talk about, and Isaac Newton, of course, Sir Isaac Newton. So Maxwell took this understanding and he developed the first ever atomic or molecular theory known to humankind. So James Clerk Maxwell, one of the greatest, I mean, this is not even his greatest work. You know, the man only lived to be 47 years old. 47 years old, and in that time, he is responsible not only for the kinetic theory of gases, which honestly would be enough to make him one of the great physicists of all time, but he didn't stop there. The entire electromagnetic theory, which is going to be a large part of what you study in physics too, is due to Maxwell. Right, and so I'm going through pens like crazy. So James Clerk Maxwell. So the great James Clerk Maxwell, one of the greatest physicists who ever lived, certainly the greatest physicist in the 1800s. James Clerk Maxwell was a Scottish physicist. Some people call him the Scottish savant. A lot of good stuff going on in Scotland here. Scottish theoretical physicist. Responsible for the first ever atomic or molecular theory of known to humankind. We have the privilege of studying it here. And it is the kinetic theory of gases. Now I'm going to give I would say a simplified derivation of the kinetic theory of gases, but it's very beautiful. And what I'm going to actually prove to you, and I've said this before, but that temperature, as I've said, is a measure of the average kinetic energy of the constituents of a substance. We call it the thermal energy. Well, I'm going to prove that in a few minutes regarding gases. All right, so let's get going on a simplified derivation of the great work of James Clerk Maxwell. All right, so I'm going to start off real simple and draw a box. I'm going to draw a box here, and so I can how good of a job I can do. We're going to let this box have an area A. We're going to say it's uniform throughout. We're going to say this box has a length L. We're going to say that the axis along L is the x-axis. And then let's see, x cross y is z. So we're going to say that this direction is y. And straight to the top is z. All right. So this area is in the YZ plane. And we're going to let there be one particle, one atom. It's going to be a monatomic theory. I mean, one atom that is literally going entirely in the x direction. All right. So we're going to say that let there be let there exist a single atom in the box. And this atom moves perfectly in the x direction with a velocity v sub x. Okay, it performs, the atom performs perfectly elastic collision. Off of the walls of area A in the YZ plane. So it's just going to bounce back and forth perfectly. Bounce off the wall, go all the way across the other side of the box, bounce off that wall, go again to the original side of the box, bounce off that wall, back and forth, always at v sub x, always at a constant velocity v sub x, making perfectly elastic collisions with each of the walls of area A, where these walls of area A are in the YZ plane. Now, let's take a look at one of these collisions. Well, and we're going to focus on the front wall, the wall that's closest to you in this drawing. All right, so let's focus. Let us focus on a collision of the atom with the wall closest to you in the picture or in the diagram. Now, I know from Newton's second law of motion, Newton's second law, we know that the force is the time rate of change of the momentum. Well, the particle, the atom's going to have a momentum mv. Before it hits the wall, it'll strike the wall with a perfectly elastic collision, and it'll come back with a momentum negative mv. So its change in momentum will be mv sub x minus a negative mv sub x, all divided by delta t. Or that force will be 2 mv sub x over delta t. Okay, so it's going to have a twice mv sub x and a time delta t from Newton's second law. Now, one thing we know is that there's not going to be any force except only at the time of the collision, and the force will be fairly good, or fairly large. What we want to do is kind of consider an average force. And of course, the force right at the collision will be very, very hard to calculate. And so we want to consider an average force. All right, and so in that case, kind of write this out here. I'll leave this information down here. So again, as we know, F is going to be 2m v sub x over delta t. I'll put that in the parking lot for a minute. Now, the only time there will be a force is at the instant of collision. The instant of collision. And this force will be large and pretty much impossible to calculate. All right, so we want to consider an average force. So instead, let's consider an average force. Between collisions of this front wall. Of area A. So we want to let the atom strike this front wall, go all the way back perfectly in the x direction, strike the back wall, and then come all the way back and strike the front wall again. We want to consider the force as being averaged over that amount of time. The time it takes the atom to strike, rebound off the front wall, go all the way back and rebound off the back wall, and then come back to the front wall again. Okay, that amount of time would be, how do we calculate that? What's the distance? Well, again, it would be going, bouncing off the front wall, and all the way back to the back. That's 1L. Going all the way back to the front wall again is 2L. So if I do distances, velocity times time, I'd have what? I'd have 2L is that velocity v sub x times that amount of time delta t. Well, if I solve for that time, that means that delta t will be what? 2L over v sub x, right? So again, real easy chapter 2 type math. And what I can do is I can substitute that into the original force equation. So I'm not going to consider the actual force at the collision of the front wall. I'm going to actually consider an averaged force. So let's put that in there. Instead of delta t, I will put 2L over v sub x. And my force now, I'll put an over bar. It becomes an average force. All right. And so let's clean this equation up a little bit. So 2's cancel out, and I can write that F bar is equal to m v sub x squared over L. All right, so that is averaging it for over F. But again, if I'm averaging, I need to fix up a couple things as well. If we're considering, So we really don't have just one atom, right? We really have cap n atoms. So we really have a large number, cap n, of atoms. And so we need to employ statistics. And consider the mean of the v sub x squared over bar, or the v sub x squared of atoms. Average over all the atoms, all n atoms, you know, adding up all their squares and dividing by cap n, or we would refer to this as v sub x squared over bar. So I've fixed this up a little bit. Want to allow for there to be n of these atoms. So I'm going to multiply by n to allow there to be n of these atoms. Then I want to talk about a statistical average of the velocity squares. Okay, now I also have 3 dimensions. In reality, an atom has a velocity v, which has components in the x, y, and z directions. Okay, so essentially what I really could say is I can use Pythagorean's theorem and say what I really have is v squared over bar is equal to v sub x squared over bar plus v sub y squared over bar plus v sub z squared over bar. I really have to account for 3 components, and I would have the average of each of the components. All right, and so keep that in mind. The other thing too is that there is no preferred direction. So I'm going to erase my picture now. So this parking lot, this, remember what we have is f bar is nm v sub x squared over bar divided by L. We also know that v squared over bar is v sub x squared over bar plus v sub y squared over bar plus v sub z squared over bar. Now, there is no preferred, there is no reason to believe that there is a preferred direction. There's no direction that is special. We don't have any reason to believe that. They're all at random. So this means that any of these statistical squares should be equal. I can believe that v sub x squared over bar is equal to v sub y squared over bar, which is equal to v sub z squared over bar. There's no preferred direction. So what this means then is that, well, if they're all equal, can't I write this? Can I write v squared over bar is v sub x squared over bar? Hey, v sub y squared is the same as v sub x squared over bar, right? So plus another v sub x squared over bar. And hey, v sub z squared over bar, that's also equal to v sub x squared over bar. So I can also write in its place, substitution, is again a v sub x squared over bar. Or I can write that v squared over bar is equal to 3 v sub x squared over bar. Or I can write that v sub x squared over bar is 1/3 v squared over bar. So what I can do, instead of having the average force formula expressed in simply as in terms of a single, as a mean of the square of a single velocity component in the x direction, I can actually generalize it and substitute instead 1/3 v squared over bar. So let's do that. If I do that, I stick a 3 in the denominator and I get rid of this little x. My formula ends up looking like this, that f bar is n, cap n, m, v squared over bar divided by 3l. That is me allowing for there to be n monatomic atoms of mass m. The mass is, this mass m is the mass of a single atom, all right? And they have an average, they have if I add up all of their v squares and divide by n, that's the average of all the v squares, all the squares, and divided by 3l, and l is the length of my box. Now, I'm talking about a fluid. So when you're talking about a fluid, it makes no sense to talk about force, right? Back in chapter 11, we're talking about a fluid. We really want to talk about pressure. So we want to use pressure instead of force. In a fluid. And when a gas, an ideal gas is a fluid, right? So how do I figure that out? Well, I know the pressure is force divided by area, right? That's how it's defined. Well, if I cross multiply, I can write that, well, force is really going to be, instead, it's going to be a pressure times an area. Instead of your average force, what I can do instead is write that force as a pressure times an area. And let's divide both sides by the area. Divide by the area, I have pressure. And I'm using a lot of P's here. I've already used momentum. This now is pressure, okay? Keep that in mind. So keep your P's, keep track of your P's. So now we're talking about pressure. Pressure is N mv squared over bar divided by 3 AL. All I'm doing is just dividing both sides by A. Oh, look at this. A times L. What's that? That is the volume of the box. So P, pressure, is N mv squared over bar divided by 3 cap V. So again, these are different V's. V is the volume of the box. And I can, cross multiply again, and I have an expression for the ideal gas law. The pressure times the volume is N is 1/3 N m v squared over bar. Here is an expression for the ideal gas law. I already have one ideal gas law, but here's another one. Again, I assumed that the gas in this box is ideal. It's a monatomic ideal gas. Now we are assuming that the gas in the box, again, a gas is just an arrangement of something, atoms, electrons, whatever you want to call it, in a space, in a volume. So in this case, it's atoms. And a gas, so we're assuming that the gas is a monatomic, means single atom, ideal gas. All right, so we have a new expression for the ideal gas law. And hey, remember we had a previous expression for the ideal gas law, right? We also knew that PV was equal to NKT. So why don't we combine the two and eliminate PV? All right, so let's combine the two. We have the one that we knew from the 1700s, and we have this new one from Maxwell's theory. So eliminating, we can say that PV is, let's see, it's cap N, 1/3 cap N mv squared over bar is cap N KT. I can cancel out my cap N's. Those are the number of atoms. And I can write that mv squared over bar is 3KT. And I'm going to multiply both sides by a half because I can. So I can write that 1/2 mv squared over r is 3/2 KT. 1/2 mv squared over r, 1/2 mv squared. That is a kinetic energy. This is the average kinetic energy of the atoms in this volume. And it is simply equal to 3/2 KT. So T is the Kelvin temperature. And I've proven two things. Number one, I've shown you that I can obtain the average kinetic energy of the atoms in an ideal gas, monatomic ideal gas. This is Boltzmann's constant. This is the temperature. If I can measure the temperature, I can measure the average kinetic energy. This is called the thermal energy. The other thing I've proven to you is that, as I said I would do so on chapter 12, is that the temperature. Now people don't, what is a temperature? And it's just this thing that I measure and I know how hot something is, right? Well, that's not the temperature. That's a use of the temperature. The temperature is actually a measure of the thermal energy of the constituents in a system. It is the measure of the average kinetic energy of the system, of the constituents. So it's only different by a constant. So when you take the temperature, what you're actually taking is, or you're determining the average kinetic energy of the atoms or molecules of the constituents, or the atoms or molecules in that system. This is a very, very beautiful and extremely powerful success in humankind, done by James Clerk Maxwell. Now, the thing about it is, you have so many atoms in a vessel of gas. There is no way you can have a quantum computer. It doesn't matter. You have to use statistics. Statistics oftentimes will tell you things that you cannot know any other way. And so we always know, statistics. Some things you can only know through statistics. And so, knowing this, for instance, let's just go back and figure out, well, how fast are these molecules going? So I know that v squared over bar was. Let's go back to this equation and figure out what's the average velocity of these atoms. So what I'll do is I'll go back to here. I'll multiply by 2, and again I'm back to where I was. mv squared over bar equals 3KT. Let's divide both sides by m, and I find out that v squared over bar is 3KT over m. And I will now take the square root of both sides. Now, when I take the square root of both sides, I calculate what's called VRMS, equal to the square root of 3KT over m. RMS, what's that stand for? Root. RMS is root mean squared. So let's kind of take a look at what we have here. We have b squared over bar. That is what? That's the mean of the squares, the mean of the squares, all right? And so you add up, so you imagine all of these atoms in your vessel. You add up all of their velocity squares, all the squares of their speed. You add them all up. You know, kind of like if I was taking an average of your exam scores, for exam 2. What do? Well, there's 20 of you. I add up all the exam scores. I divide by how many of you there are. And so same thing here. I add up all the squares, all the atoms, add them all up. Divide by how many atoms there are. That's what that is. That's the mean of the squares. And I take the square root of that. That's the root. Root mean squared. This is a square of a speed. This is a speed. VRMS is a very special speed in that not all, this is a form of it's kind of like a statistical measure, like an average. So if I imagine for a moment that not all atoms will be at this speed. In fact, they'll be distributed according to a probability distribution. We call this the Maxwell-Boltzmann distribution. And so there's another thing is we have to do statistics now. With the Maxwell-Boltzmann distribution of velocity or speeds. So the speeds of the atoms are distributed according to the Maxwell-Boltzmann distribution. This is a probability distribution. So on the vertical axis is probability. And on the horizontal axis is speed. Looks kind of like, if I can draw this, looks kind of, it's a little skewed. A little longer tail on the far end. So this is the velocity, this is the speed axis, and this is the probability axis. So the question is, now, the most likely velocity, if I just go pick a velocity at random, the one that's most likely is the one on the peak of the curve. We would call this V sub P for peak. That's the most likely one. And VRMS is sitting right around here. So again, the corresponding speed would, in this case, would be VRMS. This corresponding speed is V sub peak. All right, so this is, now, most of the velocities are going to be in the fat part of the curve. Very few will be very fast, and not very many will be very slow. Most of them, if you go and pick statistically, they're going to be right around the average or VRMS. So this is a distribution. Most things in the world are distributed according to some probability distribution. For instance, human heights or IQs. For instance, if I were to say, you draw, your typical IQ scale. For instance, you say, okay, well, in this case, it's a normal distribution or a Gaussian distribution. You have the bell-shaped curve. And so your people's average IQs are around 100. You get most people in the population, they're around 100. If you want to get somebody who's considered a genius, that's 140. 140 is way out here. People like Isaac Newton, Albert Einstein, they're kind of way off on the very, very, very thin part of the curve. So very few people are really, really, really smart, and very few people are the opposite. Most people are right around the fat part of the curve. And again, people's heights, you have very few people who are like Shaquille O'Neal or 7'3" or whatever. You also have very few people that are like Tom Thumb. You have most people are around the average. Everything's statistical. If you remember your movie Jurassic Park, the scientist said, I know these dinosaurs are being born because their sizes are in accordance with a normal distribution. So again, when nature does everything according to the distribution. Statistics is in everything, and so he was able to understand that these dinosaurs are actually are coming about via live births because because they are adhering to the normal distribution. So again, there's a statistical distribution throughout, and even in the speeds of atoms in a gas vessel, they're also distributed. And this is not normal. This is a skewed distribution. But again, I'm not going to bother writing down the form of the distribution to be on the scope of this class. But understand that there is a statistics involved with the speed of gas molecules. All right, let me do a few problems. OpenStax 13.39. That says some incandescent light bulbs are filled with argon gas. What is VRMS? Near the filament, and this is one of those things that always blows me away, the temperature of these filaments. Never knew how hot they were. Near the filaments. Assuming their temperature is 2,500 Kelvin. I still have a hard time believing it. Okay, some incandescent light bulbs are filled with argon gas. What is VRMS? We're just got done calculating. Near the filament, assuming their temperature is 2,500 Kelvin. All right, so what do? Well, let's start off with the form for the VRMS. Okay, so I'll kind of keep in mind what those numbers are. 2,500 Kelvin is the one that you really need, and you also need to understand that it's argon. So VRMS, remember, is the square root of 3kT over m. So you need T and you need M. K is the constant of the universe. All right, so T, well, that's easy. That's 2,500 Kelvin, and it's in Kelvin as it needs to be. So you're good there because the Boltzmann constant is in joules per Kelvin. So that's done. What about the mass? Well, again, it's the mass of one argon atom. Remember, it's the mass of each atom. Well, I can look at the periodic table for argon. So for argon, and one of the noble gases, I look in the periodic table, and the periodic table will give you the molar mass. That's the mass of a mole of something. Every single mass that you see in the periodic table is a molar mass. It's the mass of 1 mole of this, right? And so I look this up and I find out that it's 39.96 grams per mole. Again, that's what you see in the periodic table. You see how much a mole of this substance is, and it's always going to give you a value in grams. Periodic table is written, to benefit chemists. All right, 39.96 grams per mole. So we need to get into physics now. So a kilogram has 1,000 grams. Okay, so the grams cancel. And of course, a mole has 6.02 times 10 to the 23 atoms. All right, moles cancel. So now I have kilograms per atom. So that when I calculate all this out, I'll figure out how much, what the mass of a single argon atom is. So when I do that calculation, I find out that the mass of a single argon atom is 6.64 times 10 to the negative 27 kilograms. Oops, I'm sorry, 26 kilograms. 6.64 times 10 to the negative 26 kilograms. Okay, and that's what I need in the theory. I need to talk about individual atoms. All right, so that's what I have. I'm ready to go. So I'm ready to put it into BRMS. So BRMS is the square root of 3. Boltzmann's constant in the universe, is 1.38 times 10 to the negative 23 joules per Kelvin. T, I'm told, is 2,500 Kelvin. And I must divide by the mass of a single argon atom. That will be 6.64 times 10 to the negative 26 kilograms, and everything must be under the square root. So all this, everything goes under the square root sign. And I think I have enough room to write the final answer. BRMS, pretty fast, 1.25 times 10 to the third meters per second. Basically 1.25 kilometers per second. That is very fast. Your argon atoms are whipping around in there very quickly. 1.25 times 10 to the third meters per second. All right. Let's do 13.41 of open statics. All right, says part A. What is the average kinetic energy in joules of hydrogen atoms on the 5,500 degrees Celsius surface of the sun? B. What is the average kinetic energy of helium atoms in a region of the solar corona? I almost hate saying that word anymore. Where the temperature is 6.00 times 10 to the 5th Kelvin. Okay, so again, what is the average kinetic energy in joules of hydrogen atoms on the 5,500 degrees Celsius surface of the sun? And what is the average kinetic energy of helium atoms in a region of the solar corona where the temperature is 6.00 times 10 to the 5th Kelvin. Okay, so this actually is a very straightforward calculation. So let's kind of go back to how do you do this in the first place? Talk about average kinetic energy. So, and this is the result of the derivation of the Maxwell theory. And we learned that the average kinetic energy of atoms in a system or molecules in a system that is an ideal gas is actually going to equal 3/2 kT. Again, we're assuming a monatomic ideal gas. Well, interesting. We don't have to have any idea what the atom is. Nowhere in there is there going to be information about the atoms being hydrogen or helium. I just have to know what the temperature is. And I have to know what the Kelvin temperature is. So 5,500 degrees Celsius, well, that doesn't do me any good, right? I need to add 273 to get that value in Kelvin. So that would be 5773. Okay. So with that said, the average kinetic energy is going to be 3/2 times 1.38 times 10 to the negative 23 joules per Kelvin times 5773 Kelvin. The average kinetic energy of the hydrogen atoms on the surface of the sun. You work this all out, you get 1.20 times 10 to the negative 19 joules. Part B, if I want the average kinetic energy of the helium atoms in the solar corona, again, it would be kinetic energy average 3/2 kT, 3/2 times 1.38 times 10 to the negative 23 joules per Kelvin. In this case, this time I was actually given the straight Kelvin temperature of 6.00. Very, very hot, times 10 to the 5th Kelvin. The average kinetic energy of the helium atoms in the solar corona is 1.24 times 10 to the negative 17 joules. There you go. All right, I'm going to do one more problem for the kinetic theory. We'll talk about one more small topic. I'm going to look at problem Opus X 13.42. And we're in chapter 14 in our book, but this information was covered in the latter part or parts of chapter 13 in the OpenStax book. All right, so don't get confused by this. We are in chapter 14. All right, the escape velocity. Of any object from Earth is 11.2 kilometers per second. Okay, A. Express the speed in meters per second. And in kilometers per hour. And this is just nothing more than a conversion question. B. At what temperature would oxygen molecules molecular mass is equal to 32.0 grams per mole. Grams per mole, have an average velocity equal to, or VRMS equal to the Earth's escape velocity. Of 11.2 kilometers per second. Okay, so the escape velocity of any object from the Earth is 11.2 kilometers per second. A, express the speed in meters per second and in kilometers per hour. B, at what temperature would oxygen molecules, molecular mass is equal to 32.0 grams per mole, have an average velocity VRMS equal to the Earth's escape velocity of 11.2 kilometers per second. So a couple things to point out. First of all, what is escape velocity? Well, we've covered this before, back when we talked about gravitation. It is the velocity that any object leaving the Earth needs to exceed. And any object, I don't care what it is, like it could be a spacecraft or a space probe or whatever, must have a velocity that's greater than or equal to 11.2 kilometers per second. It is a tremendous velocity to get something to leave the Earth. Anything. Okay, that's what escape velocity is. Again, I gave you a calculation on how we can do that. And then what temperature would oxygen molecules? Remember, oxygen, if you look up oxygen in the periodic table, it has a molecular mass of about 16. And you say, why is it 32? Well, because oxygen occurs naturally as a diatomic molecule, O2. And so 16 times 2 is 32. So again, we're talking about how oxygen actually appears in nature, and it is as a diatomic molecule. You have an oxygen, and you can imagine kind of a spring in between them, and another oxygen. These are the atoms, right? Two oxygen atoms. That's how they appear. All right, and the thing is, we want to see what temperature would these oxygen atoms have an escape velocity or have a VRMS around that of the escape velocity of Earth. Now, this is actually a real problem for some atoms. So, for instance, the Earth is not big enough to hold helium, hydrogen and helium. Hydrogen and helium will escape the Earth. That's why we don't have any in our atmosphere. Fortunately for us, bigger gas atoms like oxygen and nitrogen cannot attain this kind of escape velocity and do not escape the Earth. So hence the Earth is big enough to hold an atmosphere. Celestial bodies like the moon cannot hold an atmosphere. It's not big enough. Escape velocity is such that all the gases will just escape. All right. And so we want to see, what temperature would this actually be a problem? All right. So first of all, let's take part A. It's just nothing but simple conversions. So we'll knock out part A, and then we'll look at the interesting part of this, and that's part B. All right. So part A, we want to just write 11.2 kilometers per second in terms of kilometers per hour. So again, V is 11.2 kilometers per second. Well, we want kilometers per hour. Well, we know that there are 3,600 seconds in an hour. And so if I do that, I can write this as 4.03 times 10 to the fourth kilometers per hour. All right, so let's do that. And I want to write in meters per second. So again, I start off with a 11.2 kilometers per second. This time, I mean, before I changed time, this time I'm going to change length. So there's 1,000 meters in a kilometer. Kilometers cancel. And I simply have 1.12 times 10 to the fourth meters per second. All right. I actually want to use that value for this problem. So I'll parking lot that value for a moment. All right. So I'm done with part A. I'll just put this one in the parking lot. And again, part A was nothing but a unit conversion question. So in the parking lot, I'll put V is 1.12 times 10 to the fourth meters per second in the parking lot. You go. All right. Part B. Now I want to figure out when does VRMS, or what temperature does it equal V escape? All right. So again, I have to make a determination. So what is VRMS? Well, again, VRMS is the square root of 3kT over m. M is the mass of a single oxygen molecule. We're going to treat it as a monatomic ideal gas. So again, it's really a diatomic molecule, but we're going to treat it in this problem as a monatomic ideal gas. Okay, so it's going to behave that way. And we want to say, well, we want this to equal velocity escape. Okay, that's what we want to have this equal. So let's square both sides. So I have 3kT over m is V escape squared, and solve for T. T, the temperature I'm looking for, will be m V escape squared divided by 3k. Okay. Now, let's see. I know the escape velocity. Of course, I know Boltzmann's constant, but I have not yet determined the mass of an oxygen atom. Or sorry, take that back. Oxygen molecule. So I got to find that, right? So let's determine that real quick. The mass is going to equal the mass of an oxygen, basically a mass of O2, oxygen molecule. So we know that's, even though the periodic table says 16, we know that 16 times 2, there's 2 atoms, it's going to be 32. So we have 32 grams, and it always tells you grams per mole. That's what the periodic table always tells you. And I have to do the same kind of deal as before. I want to go to physics now. So I know there's 1 kilogram has 1,000 grams. Okay, grams cancel. And I know that a mole has 6.02 times 10 to the 23 atoms, or whatever, in this case, molecules. And remember, mole is so much of whatever. I mean, it's like a dozen eggs, or whatever. I can have a mole of eggs, I can have a mole of whatever. In this case, what are we talking about? We're talking about molecules. So that means that a molecule, a single molecule of oxygen, a single molecule of O2, has a mass of 5.32. I do this calculation. times 10 to the negative 26 kilograms. A mass of 1 O2 molecule. Great. Now I can do the calculation. So I have, going back to this calculation, I have 5.32 times 10 to the negative 26 kilograms. Escape velocity, well, we calculated that earlier, right? It's 1.12 times 10 to the 4th meters per second. Don't forget to square that. Divided by 3K, K being Boltzmann's constant. 1.38 times 10 to the negative 23 joules per Kelvin. If I do all of this, I find out that I have to have a pretty high temperature. My temperature would have to be, put it up here, it is. Temperature for all this, once I calculate it, it has to be 1.61 times 10 to the 5th Kelvin on the order of the sun. So we don't have to worry about losing oxygen. We'd have to attain a very high temperature to do that. All right, that's the last problem I want to work on in this section. The last thing I want to talk about is I just want to introduce what are called PV diagrams. All right, so, and those are very, very important diagrams for studying of thermal systems. We're going to talk about PV diagrams a lot in chapter 15. All right, so the last topic is PV diagram. Well, let's go back to, well, let's go to a picture of a piston with a gas inside. All right, so let's imagine I have a cylindrical piston like in your car. So that this has an area A. There's a gas inside this cylinder. And here we're going to imagine that there is, imagine that initially I have a piston located about right here. I'm going to say the piston is going to move. So here is my initial piston, and it's going to displace up to here. So it's going to displace by some amount x. Okay, and we're going to say that, so the work, there's going to be, so essentially there's going to be a force that the gas will have had to push up on the piston to displace it. Okay, this amount what is called work. So again, we're going to do what's called work, and remember, work is what? It's really a force times the distance. Okay, yes, I know there's a cosine of the angle in there, but again, the force and the displacement are aligned, so I'm not going to worry about that. But I don't use force in fluid systems, right? I use pressure. I remember the force, the pressure is the force divided by the area. There's a pressure in this gas. So instead of this, I would say that, well, I can instead of writing force, I can write pressure times area. And instead, I can write that the work, we'll say this is a delta x. Say the work is really going to be, instead of force, P, A, delta x. A times delta x. We'll have an area displacing by an amount delta x. That's a delta volume. So the work is really going to be pressure times the change in volume. This is how you calculate work in fluids. Work in fluids is a pressure times the volume. You know, in translation, or in solid mechanics, it could be force times displacement. In fluids, it's pressure times volume. So what's interesting, remember we talked about the ideal gas law? What I really have here is a work energy theorem. I'm saying that the work in ideal gas, remember KT or 3/2 KT is an energy. So there's a work kinetic energy theorem going on with the ideal gas law. How, little would you know when you wrote the ideal gas law down, you're actually making expression, a work energy expression. That's really what it is. So work time is pressure times volume. So it's very important. So we're gonna find out that in thermal systems, the two energies of importance are work and heat. We'll talk more about this in chapter 15. So work is very, very important in thermal systems. We're gonna develop what are called heat engines in chapter 15, and you calculate the work. It's very important, to understand it. So we're going to do a lot with PV diagrams. PV diagrams, force displacement diagrams, it's equivalent of their force displacement diagram. So when you have a PV diagram, it's like you remember work was the area under a force displacement diagram. So again, work is the area under a force displacement diagram or graph. Well, in fluids, work is the area under a PV diagram. You have a PV curve or PV curve. You have a PV curve. The area underneath that is the work. Very important when you're talking about developing heat engines. All right. So anyway, this will all be this discussion in chapter 15. So the idea is it's very important for us to consider PV diagrams. Well, our first PV diagram, as I mentioned earlier, was the ideal gas. Let's look at the ideal gas law a little more carefully. Now let's assume for the moment a constant temperature. Let us hold the temperature T constant. What happens now? Well, the number of atoms or molecules in the gas is a constant. We're going to assume that. K is a constant. That's always a constant. It's Boltzmann constant. And we're holding T constant. So what we really have here is PV equals some constant. Or we can write that the formula is really P is C over V. C is a constant. Well, what does that look like on a PV diagram? But before you answer, let's help ourselves out by going back to Algebra 1. Let's go back to Algebra 1. And my vertical and axis was always Y, my horizontal was always X, all right? For whatever reason, algebra. I want to ask you a question. What is the formula? What does the curve Y equals 1 over X look like? Well, first of all, it's a rational expression. So, a rational meaning fractions. That means I have to look at any place where I can get in trouble. One of the places I can get in trouble is dividing by 0. So I cannot divide by 0. I have an asymptote at the y-axis is an asymptote. I cannot actually the function's undefined at that location. But if I imagine, what does undefined mean to a physicist? Well, if I take x to be very, 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 very small positive number, 1 over a very, very small number is a big number. So near the asymptote, the function is huge, but very close to y. Now let's pick a spot. Let's pick 1, 1. X equals 1. Let's see what that looks like here. I'm going to go with x equal 1. Well, if x equals 1, y is 1, right? So I know that the function takes on this point 1, 1. And if x gets very, very, very large, 1 over a very large number is a very small number. So the curve looks something like this. It starts off along the axis, it goes through 1, 1, and then asymptotically approaches the x-axis. We refer to this as a hyperbola in mathematics. A hyperbola. Okay, well, what happens if I try to graph y equals 2 over x? Well, similar thing. If x is very, very small, again, you're going up along the y-axis. If x equals 1, y equals 2 this time. So again, this is for you get the point. So, and if x gets large, you get near the x-axis. So you end up looking like this. And if y equals, and a constant is now 3, well, now you go through the point 1, 3, and you have another hyperbola. And you have a family of hyperbolas. Well, this is the same thing over in the PV space. What we have now is we're not x, y, but now we are going to be volume versus pressure, and we're going to see a set of hyperbolas if you have this situation going, where if PV equals a constant. All right, and each of these, this would be some sort of a T1 or a T2, a T3, any constant T. These are all called isotherms. Iso meaning same, therm meaning temperature. So if you have an ideal gas at a constant temperature, you're holding the temperature constant and you're varying pressure and volume, holding the temperature constant. If that is the case, one of the tests that you have an ideal gas is if you form a hyperbola in PV space, if the pressure volume curve is a hyperbola. That is one of the tests that the gas is ideal. So let me put up a diagram for you. I'm going to share my screen. We'll look at some PV diagrams. Now, I'm looking at the left figure. You see that toward the top, you have hyperbolas. You have hyperbola of T5, T4, so on and so forth. As you reduce in pressure and reduce in volume, you see the lower curves, they start breaking down. You start seeing a breakdown from hyperbolic behavior. And eventually you start seeing liquefaction. And when you start seeing liquefaction, you start seeing a very drastic reduction in volume once the liquefaction begins. All right, and so in that case, you no longer have an ideal gas. Once you start seeing, like even on the curve T4, T3, T5 and T4, the PV diagram, the gases look to be ideal in those conditions. When you get to T3, you start seeing a breakdown from ideal gas vapor. So when the temperature is T3, the gas is no longer qualifies as being ideal. You have to use a different equation of state, like let's say van der Waals or something. But you no longer are going to be an ideal gas law will no longer apply. All right, and so again, that's one thing to look at. So again, we're going to continue when we go to chapter 15. We're going to continue talking about PV diagrams. With that, I'm going to close the lecture for chapter 14. So I'm going to stop sharing, and then this is it for the lecture.